All right, thank you, Ben. All right, good to see you all. Good afternoon. So we're going to start off the afternoon with Philippe Francesco, who will tell us about triangular ice, combinatorics, and limit shapes.
Thank you. So first of all, I would like to start with an apology. I'm apologizing for not being there in person. I couldn't split myself in two, so I'm talking from Florence, Italy right now. It's 10 p.m. Okay, so but I still thank the organizers. So today, the subject will be sort of generalizations of a big part of the alternating sign matrix saga. And the generalization is just to switch from square lattice to triangular lattice. Okay, so in a nutshell, that's what it is. So I'll try to explain a little bit the background. First, I have to go through a little bit of things on alternating sign matrices, of course, connections to a six-vertex model, role of integrability, and then we'll see what happens on the triangular lattice. And there we'll start the combinatorial wonders. So there will be connections to tilings, domino tilings of strange domains. And I'll show you a proof of one of those results, and then a bunch of conjectures and open problems related. And finally, we'll go to the asymptotic version, which is you look at very large domains and very large configurations, and you ask questions about what does a typical configuration, very large configuration, look like. And in the systems I'm going to introduce, we'll have this Arctic phenomenon again, but very interesting Arctic phenomenon, as you will see. Okay, and with all sorts of questions also attached. Okay, so that's the program. And to just give you an appetizer here, I give you three sequences which are going to appear in this talk. So you might already know some of them, but if you don't worry, you learn. Okay, so here is the story of alternating sign matrices in a nutshell. So it starts in physics as usual, and it starts with trying to describe water, or rather frozen water, that is ice, in 2 dimensions. So you imagine that, well, water is H2O, right? So you have 2 hydrogens for its oxygen. You imagine that you have oxygen ions on the vertices of a square lattice. And then you want to dispose hydrogens in such a way that an oxygen would be always closer to 2 hydrogens. And let's say they slide freely along edges of a square lattice. So you get a configuration like this. Okay, so if you replace the data of ions by their dipolar momenta, it gives you this. So small arrows, which point, where the electric dipolar momenta are pointing. Okay, and so the rule here is that at each vertex, there are exactly 2 entering arrows and 2 outgoing arrows. And it's called the ice rule for obvious reasons now. Okay, so on top of that, we're going to choose boundary conditions. So let's say take a square grid n by n and choose boundary conditions that guarantee the existence of what's called domain walls in physics. A domain wall is just a place where arrows are going to be reversed. So the best way of forcing arrows to reverse is to force a boundary in which arrows are already reversed, right? So somewhere in the middle, they have to be reversed. So you create those domain walls, and the existence of those domain walls is the interesting physical aspect of this model, which will be responsible eventually for part of the Arctic phenomenon. Okay, so we have these boundary conditions called domain wall, and so everything horizontal enters, everything vertical exits, and on top of that, there's this ice rule, a local rule at each vertex, but there are exactly 2 entering and 2 outgoing arrows. Okay. All right. So there are several ways of describing the configuration. So the first is the arrows. Okay. The second is quite interesting, is with paths. So how do you define those paths? Well, you choose a basic orientation. So everybody to the right, everybody down, right? So this orientation for everyone. And then whenever locally you agree, you put a red edge, and if you disagree, you don't put an edge, right? So this one agrees fully, of course, by definition, and this one disagrees fully, right, etc. And now you make sure that your paths are going to be non-intersecting, but they're allowed to actually kiss each other, right? So you have these kissing points, and you can really see the flow, paths flowing from, say, northeast to northwest to southeast. Okay, so that's osculating paths. And finally, if you look carefully at those vertices, vertex configurations, you see that the four first, I can call them transmitters because they transmit the orientation of the edges, right? Whereas the last two are reflectors. They reflect the orientation of the edges horizontally and vertically, okay? And so the nice bijection that people found is that you can formulate the entire configuration via a matrix whose entries are 0 for all the transmitting vertices and plus or minus 1 for all the reflecting with an alternance, you know, of the rules when you go along each row and each column. So this is these alternating submatrices, and this is what this looks like. So you have three ways of looking at the same object. So these are really bijections. Okay. All right. So here is a small part of the alternating sign matrix world. Okay. So here, what we've already described. Here, actually, the counting of those objects of size n by n. And it turns out that this counting is also the same as the counting of what's called totally symmetric self-complementary plane partitions, which are just, if you want, pilings of cubes in a corner of a room, right? In such a way that when described in projection, two-dimensional projection orthogonal to 1, 1, 1 direction, what you see is the rhombus tiling, which has all possible symmetries of a regular hexagon. So you actually are looking now at rhombus tilings of a regular hexagon of edge 2n, right? With the maximal possible number of symmetries, meaning that if you look carefully, you will end up with 1/12 of the whole domain as being the fundamental domain. And the TSS CPP just count the configurations of this fundamental domain, which is then extending everywhere by reflection, rotation, etc., all the symmetries. Okay, but for today, I ask you to look rather at this picture, which is the reformulation in terms of rhombus tiling of what's called descending plane partitions introduced by Andrews and reformulated by several people, including LaSalle and Krappenthaler. So here is the thing, you again have an hexagon, right? But it's no longer regular. It alternates between n and n plus 2, n plus 2, n plus 2. And this slight discrepancy is to accommodate for a central hole, which is a 2 by 2 by 2 triangle, okay? And then on top of that, as if it were not enough, you impose a rotational symmetry by 2 pi over 3, okay? So this is a rhombus tiling reformulation of descending plane partitions, okay? And this is again counted by the same number. And this is really what we are going to generalize today. So we are going to generalize this and this. Okay, so in a nutshell, what did physics bring to this purely combinatorial problem, let's say, of enumerating configurations? It's integrability. So it's the fact that instead of just counting, you can decorate the problem and attach weights to configurations in such a way that the weight of a configuration is a product of local weight at each vertex of the configuration. And so you decide of attaching certain numbers to those local configurations, which are called A, B, and C traditionally. And mathematically, this can be packaged, if you want, into an operator which acts on tensor product of two-dimensional complex spaces, which is usually called the R matrix, and which gives rise to all sorts of models, interesting vertex models, of which the sixth vertex is only like the top of the iceberg. Okay, so we have this R matrix, and as an operator, it satisfies a cubic relation, which pictorially can be represented as follows. So first, I represent the R matrix operator just as the intersection of two lines. So it's really the dot at this intersection. Each line carries a vector space and a complex parameter. The complex parameter is called spectral parameter. So this line carries Z, this line carries W, right? So R is R of Z and W and acts between this tensor product and this tensor product. So here to here, right? And now we are looking at an identity which acts from a triple tensor product here to the triple tensor product there. And the relation expresses simply that you can basically move this line across this intersection and put it on the other side. And the resulting identity is just a product of 3 R's is equal to another product of 3 R's, which is this famous Yang-Baxter equation, of which you can find solutions. And so the sort of basic and simplest solution for a two-dimensional vector space here is the so-called six-vertex rational solution, which has the A, B, and C's I mentioned earlier, simple degree 1 polynomials in Z and W. Okay. All right. So, but the main thing here is the freedom of moving lines around. This is really what I want you to remember from all this, is that you can move freely lines around and reformulate your configurations in an equivalent way via these elementary moves, which are these Yang-Baxter moves. Okay, so one thing you can prove, for instance, for the six-vertex model, which is fully inhomogeneous, that is, you put horizontal spectral parameters which are different for every line, and vertical spectral parameters different for every column. And so let's say the vertex here at line I and column J would have the weights parameterized by Zi horizontal and Wj vertical. Okay. Well, the answer is a determinant, which you can actually compute quite easily, thanks to this Yang-Baxter equation, right? The Yang-Baxter equation, the first consequence is that this thing is symmetric in the Z's and symmetric in the W's. And then by using the very specific form of the weights, essentially the weight A, you can see that these functions here satisfy recursion relations. So symmetry plus recursion relation, that's plenty enough to prove this identity. Okay, it's called the Ezergin-Korepin determinant. Okay, so now what we are setting to do now is to port all this to the triangular lattice. Okay, so I replace my square lattice by triangular lattice. I'm going to consider a nice quote-unquote model because it's no longer H2O, right? It's something else, but okay. And the rules are going to be, I just paint orientations on all these edges, right? In such a way that at each vertex, there will be 3 entering and 3 outgoing, because now my vertices are 6 valent. Okay, I represent everything in a square lattice because it's easier to represent, and also because my boundary conditions will be better expressed in this way. Okay, so at each vertex, I have 3 entering, 3 outgoing, so a total of choose 6 free possibilities, which is 20, and that's why it's called 20 vertex model, whereas before I had 4 choose 2, which was 6 possibilities, 6 vertex model. Okay. All right, so the first people to look at this model were Baxter and his graduate student Kelland, whose thesis was about the critical version of this 20 vertex model. All right, so we're going to imitate really what was done with the 6 vertex. So first, we are going to introduce a path model, right? So these paths are going to be osculating. And the definition is exactly the same. So here I represented the 20 vertices, 20 possible configurations, local configurations. We take this as basic orientation, so everybody down to the right, right? And whenever you agree, you put an edge of path, and when you don't agree, you don't put anything, okay? So for instance, the first guy who agrees fully, I represent it in this way, and now again, it's a kissing point, right? It's still non-intersecting paths, but which are allowed to triply kiss. Okay, so it's really very French. And here only by pairs, and you have also, of course, a path which cross the vertices. All right. So you have these 20 configurations. So the paths in question are usually called Schroeder paths because they can have three directions, right? Horizontal, vertical, and diagonal steps on the square lattice. Okay, so boundary conditions now. Well, the simplest thing is to really emulate the same as we had in the 6-vertex model, which is to force those domain walls. We're going to let everybody enter horizontally and diagonally here on the west side, if you want, and enter also on the east side, and then exit on the south and exit on the north. Okay, so that's my first suggestion. Take this as domain wall boundary conditions. Now there's a problem because this guy, is he part of the west or is he part of the north? Okay, you have two possibilities. So it gives rise to these two possibilities. But then if you think a little bit, the second is actually the pi rotated of the first, right? If you do a rotation of a half term, you map the second to the first. So they're actually the same. Okay, so I gave you some examples of configurations. So now you see all your paths are going to start on the west and to end on the south, right? And all the edges are occupied. But here, the top and corner here are empty because they're of this change of point of view. But of course, if you painted instead the empty edges and didn't paint the full edges, you would end up with a configuration like this, provided you turn by half turn. Okay, so it's really the same thing. Okay, more. What you could do is actually imitate completely what happens with 6-vertex, and then only have entering arrows horizontally and exiting arrows vertically, right? And all the rest, these diagonal arrows, let's say they all blow to the northwest. Okay. So that gives you different types of configurations that have nothing to do with the other ones. It's another problem. So first problem is try to enumerate these configurations on square grids, okay? And it's rather easy. You just use a transfer matrix and you can compute these two sequences. Okay, so for first domain wall boundary condition 1, 2, and second domain wall boundary condition 3. All right. So here's the example of 23 domain wall boundary condition 1 configurations of size 3, right? So there's 23 of them, as you can count. Okay. All right. So now I want to forget about all this and look at a different problem. Okay. And my different problem is going to be a problem of tiling, of domino tiling of a certain domain, which is almost Aztec-like, but not quite. So the first thing, okay, I'll explain the name of this domain, but first I explain how I get this domain. So you consider a rectangular domain of Aztec-like, right? So with these staircases on the boundary, which is n by n minus 1, and here you remove one little square. Okay, so all this is drawn on the square lattice. Okay, so you take 4 copies of this. And now you glue them together. So what you see is that in the center, I have this cross-like hole, right? And then the whole thing looks like a square with a little bit of defects, like 4 defects around the square. Okay. So the whole thing now I decided to call the Holy Aztec Square, holy because it has a hole, not because it's nothing religious about it. And moreover, from the construction, there was clearly these 4 pieces which I glued together. I will impose that now I have 2 pi over 4 rotational symmetry. So you see, in a sense, this guy here, I claim, is going to play the same role for the 20 vertex configurations as the descending plane partitions were playing for the alternating sign matrices. Okay, so this is my first claim. Okay, so to go further with this claim, let's try to enumerate actually the tilings. So it's not too difficult. Because of the 2π/4 rotational symmetry, you can restrict yourself to the fundamental domain, right? And actually the whole thing is folded, right? It's glued, and it's actually a nice cream, right? It's a nice, just like there are many in Florence around me. So this is nice. So you just glue this side to this side, and then you want to find the number of domino tilings of this object. But there was this cross in the middle. So it means that you forbid from having dominoes wrapping around here, right? So it means that your ice cone has a hole in the bottom. Bad news. So it means you have to eat very quickly if you don't want to make any disaster. And now, how do you count? Well, you use the standard dictionary between dominoes, which are bicolored, right, naturally, and again, paths with vertical, horizontal, and diagonal edges. So the same Schroeder paths that we were discussing before. But now, non-intersecting really, no kissing allowed, right? Because of the structure of the domino tiling, they are really non-intersecting. Okay, so to count that, the fact that you have identification of these two lines means that those positions and those positions are, well, not exactly the same here, but differ by one because of my choice of rulers. Okay, but anyway, the theorem is very easy to obtain. The counting is actually a determinant, à la Gesell-Vienno, of a certain matrix, which I prefer to code the matrix via the generating functions of its matrix elements. So it's an infinite matrix, if you want, right? Whose ij term is just the ziwj coefficient in the series expansion of this function. Okay, so it's just a compact way of presenting the matrix. The nice thing is that n is just the truncation. N doesn't appear anywhere in the matrix. And for 6 vertex, some similar things are going to happen. All right, so why is this the right matrix? So this is the generating function for the elements of the identity, of course, right? And so why is determinant of identity plus m the right answer? It's because of Cauchy-Binet. We know that the determinant of identity plus m expands into diagonal minors of the matrix M, right? And now these diagonal minors, by Gesell-Vienno, we can identify them with the counting of configurations in which we pick these row indices and these column indices here, right? And you just have to figure out the matrix that generates all these different pieces of path. And already we can see that there should be a determinant of the form 1 minus z minus w minus zw to generate all these guys. And indeed, it's right here. The rest is decoration. So this formula works really nicely and you can apply it. And so just for an example, I show you that I get 23, which is the number of size 3 configurations of this holy Aztec square with 2π/4 rotational symmetry, given by determinant of identity plus this matrix, and it gives you 23. So conclusion, 23 equals 23, right? So these 23 configurations, okay, well, I would like to be able to biject them with these 23 configurations, okay? Actually, the conjecture is that, of course, the two things are counted by the same number. All right. So how do I prove it? So the proof is very interesting because it uses just integrability. So we have to come up for the 20 vertex model with integrable weights. And then by using integrability, we're going to be able to compute the partition function and show that it's the same as that determinant I just showed. Okay. So the idea is to go from 20 to 6 vertex. So how does that go? Well, first I have to define the weights. Okay, so to each local configuration, I want to associate a weight W. Okay, and here I notice that a triple intersection is not very nice, but if I push my diagonals a little bit down, let's say, I'm going to resolve these intersections into simple intersections. at which I can decide that, you see, this triangle is a new object, right? So I can decide that I paint the edges of these new triangles with oriented edges, okay, in such a way that now the ice rule is satisfied at all the new vertices, at the 3 vertices that split the 6-valent vertex, okay? And that can always be done, and you can have either 1 or 2 solutions for the orientations of these intermediate edges, new edges. So you're kind of describing your 20 vertex as a collection of 3 6-vertex model on 3 sublattices, 1, 2, and 3, indicated here, right? And this lattice, by the way, is called the Kagome lattice. So we're talking now about ice on the Kagome lattice. So how are the weights described? Well, I showed you how to pick weights for 6 vertex. So you have 3 sublattices, so 3 sets of weights, right? And now we want to define our weight for the 20 vertex as a sum over all possible inner configurations, right, of the products of those 3 weights. Okay, so it's cubic in the A's, B's, and C's, which are here. Okay, and moreover, I want that this prescription of resolving the singularity by taking the diagonals down be independent of how I resolve the singularity. So it should be the same answer if I push them up instead of down. And so in this example, for instance, you will convince yourself that if you push the diagonal up, there's only 1 configuration. So you actually and eventually get relations between the 3 sublattice 6-vertex model, which you can solve, okay? And the solution looks like this. So you get 7 different local weights, which correspond to the guys in the boxes here, right? So you have 7 classes of local weights, each receiving one of those weights here. And the parameterization is just to trade the spectral parameter ZWT for some parameters lambda and mu, and Q, I didn't mention it, but you've seen it appear somewhere. When I define the weights of a 6-vertex model, it's far away already. Here, there was a parameter Q, and this parameter Q is just a parameter of the model, right? A different Q is a different model. Okay, so very well. Now I know what weights to attach to the configurations, to the 20 configurations, in such a way that I can move lines around. And now I'm almost done. So just a remark before we go into the proof, the remark is that there's a choice of those parameters which guarantee that all the weights are going to be equal to 1. Okay, so it's a check, huh? You check that. So it means that the uniform case in which the weights are not there, in a sense, or pure counting, is also done as a particular point inside this big integrable set of weights, okay, which is good. And in that case, the 3 sublattices don't have the same weights, actually. So the sublattice 1 has weight A equals 1, B square root of 2, C equals 1, and the 2 others are A equals square root of 2 and B and C equal to 1. Okay, so these are points of the 6-vertex model which hadn't been considered before as being interesting from the point of view of combinatorics, but you will see that they play a role here. Okay, so transformation now. So I start from 20 vertex and I want to end up with 6 vertex. So what do? Well, I stretched everything. Okay, so I pull the lines, the vertical lines and the horizontal line to see better what I'm doing. Okay, and now I'm going to use my property of being able to slide the diagonal lines, right, on either side of the crossings of vertical lines. And so I'm going to slide these guys, all the blue ones, here, 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 all these, I'm going to slide up. But the red ones, I'm going to slide down. Okay, so this is just, this doesn't cost anything. Maybe I manage to go back this way. All right, so we do that. But now you have to remember that we have a boundary condition, which on the east says that all the arrows enter, and on the west, all the arrows enter, right? But we have the ice rule. So whenever we have 2 arrows entering, the next 2 should be outgoing, right? It's fixed by the ice rule. So if you think a little bit, you will see that all the arrows within this triangle are completely fixed, meaning that my partition function, which was a big sum over product of weights over the configurations, factors out a bunch of numbers, right? The product of all these numbers. These are just numbers. But and the same thing happens below, on the left, on top. So at the end of the day, you just have a bunch of numbers times what's left in the middle. And what's left in the middle is a sublattice 1, 6 vertex more, right? So here is the theorem. The partition function of a 20 vertex with all weights equal to 1 is equal to that of a 6 vertex on the sublattice 1 with the weights I mentioned before, which is 1, square root of 2, and 1 for A, B, and C. So here you see the weights square root of 2 are attached to paths that go straight. Okay? All right, so just a little pause here, showing that you always have to look in nature for answers. Instead of a Kagome lattice, here is a lattice of Kagome found in a grocery store in Japan. And it's a delicious beverage. And that beverage has a really interesting composition. It's made of 20 vegetables and 6 fruits. 20 and 6. Okay. So you just have to look carefully. And that's the answer. So example of the counting, right? So in size 3, essentially what I'm saying is that the 20 vertex configurations are counted by the 6 vertex configurations, right? Which are the 7 alternating sign matrices, if you'd like, or the 7 osculating paths. And whenever I see a straight line, I put a weight square root of 2, right? So here weight 2, square root of 2 times square root of 2. This one gets weight 8. You sum up all the weights and you find 23. Okay, so that's my 23. All right, so how do you conclude now? Well, you use the results of a determinant which I showed you before, right? So you're going to send all the Z's and W's to same values, right? And you're going to extract the value of this determinant with Q, an eighth root of unity. Q had to be, so maybe I can show you again. In the parameterization here, we needed eta is pi over 8, and Q was e to the I eta, actually 16 root of unity. So it's kind of non-standard value of Q. Just to remind you, the value of Q that did the job for alternating sign matrices was e to the I pi over 3. So 6th root of unity. Now it's 16th root of unity. Now, you do these limits in this determinant, and you end up with another determinant, which you can match with the one I showed you before. Okay, so there's a little bit of work, but it works. Okay, so that's the end of the things I can prove. Well, there's a little bit more, and now come the conjectures. So the other case turns out to be seemingly much more difficult, which is this Domino boundary condition free, right? Whereas there's half the number of paths, if you want, okay? And the numbers are given by this sequence. And if you look at the encyclopedia, you'll find that these numbers have appeared in the context of counting the domino tilings of a square of size 2n. Okay, but not directly these numbers, but the square of these numbers times the power of 2. But then, by some arguments of Chukwu, for instance, you can figure out that actually this power of 2 times the square feels very much like what your tiling is half of the object. So indeed, Parter in 97 found that you can just split your square into 2 pieces, and then the number of domino tilings of this domain is just Bn by itself. Okay. So this is another formula a la Temperley-Fisher, which dates back to the 60s. Okay. All right, but that's a conjecture because we have no idea how to prove it. So I present it to you as an open problem, right? Find a way of proving that the configurations of the domain-wall boundary condition free 20 vertex model on a square grid of size n is actually counted by the number of domino tilings of the half of the square of size 2n. But we can do better, and it's always better to have more conjectures around the same thing than just one. Okay, so we have a whole family. So here is how we extend the conjecture. Instead of looking at a square, now we look at a rectangle. So we extend it down like this, but here we put no paths at all on the extended region, right? Here we keep the same number of paths. And now we have a new parameter k, right? So it's a pentagon now, you can call it a pentagon of ice, right? And the same question, you have numbers which now depends on two parameters n and k, okay? Now, on the triangle part, what you can do is realize that this is a roof which you can raise, okay? So by raising the roof, you can see that it starts looking like an Aztec diamond boundary, right? And that's just something you can see very easily if you figure out the coding of these domino tilings in terms of Schroeder paths, as I showed you before, right? And so you see that this guy has a top Schroeder path which is very constrained. It cannot go beyond this green line, right? And this one is a bit less constrained. It can be a little bit higher. So you impose, in fact, a constraint on the top Schroeder path in your non-intersecting path configurations, okay? And now the conjecture is that I have a new parameter k now, n and k, right? And that these match. That is the pentagons of ice and k are counted by the triangles with raised roofs and k. So domino tilings of those guys, 20 vertex models on those guys. The whole family of conjecture is usually better than just one. All right, and in this family, I know how to prove one of them. Okay, so here it is. So if you send the roof to infinity and degenerate your pentagon into a quadrangle, right, the maximum possible size, then you have to compare these two models, right? 20 vertex here and domino tilings there. And there, the number of configuration in both sides is given by my third sequence, 1, 4, 60, etc. Okay? And that actually can be proved. So there's a theorem here that the two numbers are the same. And there is even a conjecture, and that's open. So another open problem, which is to prove that this number is actually this compact closed form. And now I'm sure many of you know by heart the formula for alternating sign matrix number, right? You will see here that the 3 in alternating sign matrix number seems to have been replaced by a 4, right? The 1 by a 2, and you have this extra prefactor of power of 2, right? So, but it feels very much like some cousin of the previous numbers. Okay, so the proof is the same. So I'm just going to flash you this, right? So you just move lines around because you're allowed to, because of this definition of the weights, right? And you end up not with 6 vertex, but with what is called the U-turn boundary condition 6 vertex model, which also is given by another determinant, which appears in various places, Cooperberg and Tsuchiya, for instance. Okay, so, and thanks to this, of course, you can compute on both sides, right? And compare the determinants and show everything. Okay. So in the last few minutes, I want to discuss now a sort of different aspect, which is less combinatorial and more probabilistic, if you want, which has to do with the Arctic phenomenon. So instead of describing things, I think it's better to just look at a very large typical configuration of a domain wall boundary condition 1 model. Okay. So what you see here is the emergence of certain phases, so which are frozen. Frozen means that they are invariant under translation, right? So this is empty, it's frozen to be empty. Here it's frozen with parallel lines. Here it's frozen with 2 types of parallel lines, right? In 2 different directions. Down here it's frozen with 3 types. Down here it's frozen with 2 types again, and down here it's frozen with vertical lines only. Okay, so you see all these frozen phases, and they're separated clearly by some sort of curve, which looks like a coffee bean. Okay. All right. You can actually prove that, or at least not completely rigorously, but using a method which was introduced by Colombo and Sportiello in 2016 called the tangent method. So this tangent method is very powerful. First of all, it works very well with all the non-intersecting path problems, right? But here we don't have non-intersecting paths, we have kissing paths, right? So often people will call non-intersecting paths free fermions and kissing paths interacting fermions, right? So it's one higher level of difficulty, if you want, from just trying to evaluate what happens, like, okay, the basic thing is this Arctic circle for the Aztec diamond domino tilings, right? So here it's a bit more subtle, a bit more difficult, but we're going to use this method, and the method is very simple. So first of all, what does the limit shape look like? Well, it's certainly the boundary of the empty domain here, right? So we are looking at the boundary of an empty domain. So, well, it's delimited by the outermost path, right? So the idea is to detach the outermost paths. So put this end higher up, somewhere here at the position that you predetermined, and look at what happens. And what happens is that this path now is going to actually tell us something about the other paths. So as soon as it's far away enough from the other paths, it's just supposed to follow a geodesic, which in this case is just a line, right? The most likely trajectory is a line. But when it starts meddling with the other paths, well, the thing is that it becomes the curve, right? The Arctic curve. So at the connection point, one argues that it is tangent, okay? So now, if you manage to compute the most likely position of a point B here, right? So you force the path to exit the domain somehow. So it has to exit it somewhere. So the most likely exit point, okay, will determine for you a line, which is parameterized by this distance z, to which you move the end of your path. And the envelope of those lines, of this family of lines, is going to give you the Arctic curve, okay? So how do you compute now? Well, you just have to compute two partition functions, right? One which is almost the same as the one we had before, except that now there's a path that exits, right? The top path exits somewhere, say at the position K, right? And then it's a single path, so it's just the partition function of a single path with fixed ends, okay? But the whole thing is always with ambient weights of whichever vertex model you have. So this would be what happens for 6 vertex. This would be what happens for 20 vertex, Domino boundary condition 1. And this would be what happens for the last problem I showed you, which I knew how to solve, okay? So in there, the weights that you attach locally to all the vertices of your path are the 20 vertex weights, okay? So you just have to compute this partition function, do large size estimates, and then from those estimates, you find the leading contribution to the total partition function, and it's maximized at a certain critical point here, which will be your most likely exit point. Okay? All right, so very quickly, I don't want to write any equations, but 2 equations at least. The one for the partition function in which you have put all the parameters equal, right, for the 6 vertex. Well, this partition function satisfies this relation as a direct consequence of the Lewis Carroll identity or Denano-Jacobi identity or Keough condensation identity, whichever name you want to call it. Okay, Plucker relation. And which shows you that the asymptotics of a partition function obeys actually the 2-dimensional Liouville equation. With boundary conditions, you can fix F. Okay, and the second thing is that to determine the partition function with an exit point somewhere, what you need is just to change the last spectral parameter in your last column. Okay, so instead of being V like everybody else, it becomes V plus Xi. And so it gives rise to what I call a 1-point function, which is the ratio of this guy at Xi by this guy at 0, which also satisfies a relation as a consequence of Denano-Jacobi, right? Because all these guys are determinants after all. So relations between minors of determinants, it gives you these relations. And you can also estimate the large N behavior. And this gives you a relation between the free energy that you found here And now what plays the role of the free energy for the one-point function. So having determined these asymptotic behaviors, it becomes child's play to figure out the most likely exit point. Therefore, the family of lines of which you're going to take the envelope to get the Arctic curve. So we have explicit but not very nice looking formulas for the Arctic curve, and you can see that it works perfectly with the simulation. And the white dashed line is the exact prediction by the tangent method. Okay, and now, of course, I showed you all sorts of other weights, right? It's not just the uniform case, right? Uniform case is the coffee bean, but now you can play with weights, right? And you get all these other configurations with all different interesting Arctic curves. Okay. Now, the Holy Aztec, you can play the same game because of the connection between the two problems. There's also a refined connection, which allows, in fact, to relate the one-point functions. So once you figure the one-point function, you can apply again the tangent method. And now you see that with my problem, which had a Z4 symmetry, right? I have a Z4 symmetric Arctic curve, which is algebraic, and I wrote it by pieces here, and it's of degree 10. Here is the top degree term. So algebraic curve of degree 10 in this case. And now I can put them together on the same picture. So here is my coffee bean, here. And around the coffee bean, I've drawn the Holy Aztec limit shape. And what you can see is that there's a branch here, which is common to the two problems. So they are enumerated, the configurations are enumerated by the same numbers, right? But it's more than that. It's much more than that. It's saying that asymptotically, at least in the vicinity of this top corner, they look the same, right? So I would say that as close to a probabilistic bijection as we can get, right? So I think it raises all sorts of interesting questions. One of them is what I call the shear phenomenon. I don't have time to explain, but essentially, if you take this branch, which we determined by the tangent method, and analytically continue it, so we know it will analytically continue on this degree 10 curve. Well, if you analytically continue it until it reaches this line, then you can find this part of Arctic curve by just applying a shear. Okay, so I have an explanation for that, but it would take too much time, so I pass quickly. But I want to notice for you that in the case of limit shape of alternating sign matrices, the same phenomenon happened. So if I compare now, I put on the same picture the descending plane partition limit shape and the limit shape for the alternating sign matrices, well, this portion here is the same ellipse. So for the descending plane partitions, it's non-intersecting paths. It's an ellipse. It's this ellipse. And if you take the analytic continuation of this branch for the alternating sign matrices and apply the same shear as before, you will find the second branch for the Arctic curve. So this Arctic curve for ISM is actually made of 4 pieces of ellipse glued together, right? So it's non-analytic at these points, definitely. You have some jump in some derivatives, just like we have in this problem. Okay, so same kind of thing is happening here. Okay, all right. So more open problems for the pentagon, well, quadrangle of ice. You can do the same thing, but now you have to do it with a U-turn boundary 6-vertex model, which was not actually computed, right? So I had to compute also the one-point functions for those guys, and I figured a part of the Arctic curve. But I know that something is missing here, and I have no idea how to compute it. Okay. But the funny thing is that if, again, I analytically continue the branch that I know how to compute with the tangent method, I find the same for symmetry Z4 curve as before, degree 10, right? And so I can actually put these two guys together. I know that these two are counted by the same number. I showed it to you, right? Same determinant. So now I can put the two domains on the same picture and notice that they have a common Arctic branch again, right? Branch of Arctic curve. So again, it's not as good as a bijection, but it's a sort of probabilistic bijection because actually the typical configurations look the same, at least at the boundary with a frozen face. Okay. So I should conclude now. I think I'm a little bit over time already. So I hope I have convinced you that triangular ice has interesting combinatorics. That it has an interesting Arctic phenomenon, okay, which we explored using the tangent method. But of course, tangent method is not completely rigorous. Yeah, it relied on a number of assumptions, which turn out to always be true. It's been even proven by Agarwal for a six-vertex model, right? But still, it's not completely rigorous. And there is this phenomenon of non-analyticity, which seems to be characteristic of those interacting fermions as opposed to free fermions. That is, these kissing points are really responsible for a different behavior, a lack of analyticity of those Arctic curves. So this should definitely be better understood. And finally, I end with two questions. One of them is, can one figure out loop models related to those problems? So this is a part I didn't describe, but in the alternating sign matrix saga, there's a whole part which came from physics also and became a combinatorial problem by itself, which has the name of Razumov-Stroganov conjecture. Okay. And so, okay, I have no time to explain, but it would be really nice to have a sort of version of that for this problem. And it goes through trying to find loop models, maybe web models, why not, associated to my configurations of 20 vertices. Now, maybe a simpler problem would be to try to classify the good boundary conditions. So I will call good boundary condition one which guarantees an Arctic phenomenon, right? And maybe one that we can solve, right? So I was able recently to add one more case, which I call domain wall boundary condition 3 on a triangle. So here I'm going back to the triangular lattice just to show you that what we've done here was a little bit skewed if you looked at it on the triangular lattice. And so this is a new case in which the partition function is now an Aztec-like partition function times the six-vertex partition function. So it's yet another of those objects. So it looks like this, right? You have entering edges along the diagonal here and outgoing edges here, and then you have your osculating Schroeder paths. And the theorem is that these are the numbers. And the Arctic curve looks like this. So it's a quite interesting phase diagram, right? Where you have an empty domain and the same, basically the same phases as we have observed in the 20 vertex that I was describing before. Okay. Now a very interesting open question, and I will finish with that. If you take the portion of Arctic curve that you get from the tangent method for this triangular problem and take its analytic continuation, what you find is the blue curve here, right? It's again a degree 10, but it's not the same as before because now it only has a Z2 symmetry, right? Instead of Z4. Okay, so this analytic continuation, my guess is that it should be the Arctic curve for a domino tiling problem, right? Because it's analytic, it has to be a free fermion problem. So why not a domino tiling problem? And what I see here is two Aztec squares that are kind of eating at each other, like in a Pac-Man game, right? And so they are forming this peculiar domain. And so I haven't been able to find any domain whose number of tilings, perhaps with symmetries, would give the same numbers as those, but I think it's an interesting question. Okay, it would be nice to conclude. Okay, so thank you for your patience, and I'm sorry for going over time.
Thank you so much, Philippe, for a really fun and interesting talk. Are there questions? Yeah, go ahead. Please be loud. Sorry, I couldn't even hear down here. So an analog of the eight
No, I
vertex
can't
model.
hear.
Yes, Philippe, he's asking about an analog.
I
For the
can't
eight
hear at all.
vertex. Oh, you can't. Can you hear me now?
Yeah, you I can
Okay.
hear, but not the
Great.
question.
So the question is there an analog of the 8 vertex model in this setup for the triangular lattice?
Good question. The quick answer is no. Essentially, because you see, you lose this ice condition in the 8 vertex model, and I think Baxter introduced. Let's see, there was a 32 vertex model in the book. One has to look in the book of Baxter, but I don't think anything was shown for that case. So answer is no, but maybe one just has to sit down and try to figure it out. So it would have elliptic weights and presumably addition relations for elliptic functions would play a role. I don't know.
Yes, another question? Between ASMs and.
Can you repeat?
Sorry, I'm trying to repeat. Did you hear, Ben? Do you want to see? So we're wondering if there's a bijection between.
Such a method be useful to find a bijection.
Mhm. Okay. Oh, good. Vic just put it in the chat.
I just saw the question in the.
So.
Okay, maybe I can repeat it then. Could such a technique be
wonderful.
useful in finding a bijection between alternating sign matrices and totally symmetric self-complementary plane partitions? I don't see how. And you see, my problem here is that I feel that I have stumbled upon the descending plane partitions, but I have no candidate yet for totally symmetric self-complementary plane partitions. Okay, so I think there should exist another model, right, of tiling with even more symmetries, right? Because that's what happened before. The 2 pi over 3 symmetry was for descending plane partitions, but the TSS CPP had much more symmetry, right? It had the 2 pi over 3, but it also had reflections, it had dihedral, etc. So, so I would imagine that an indicator is the Arctic curve for this Pauli aspect diameter, right? So the same Arctic curve, I imagine, could perhaps be obtained by a much more symmetrical domino tiling problem, right? And then that guy would play the role of TSS CPP. Okay. Now, does that help in any way? No, it just adds up more problems, right? More unsolved problems. I get all these equinumerous sets and no bijections between them, right? So what I'm just saying is that this sort of combinatorial wonder and bizarre thing of having different objects counted by the same number actually extends to this case, right? I'm just adding more problems.
Any more questions? All right, well, if not, let's thank Philippe again.